Okay, then, so without much ado, I'll go ahead and introduce the speaker. So, Tapia, I'm Sandeep Juneja. We've been in touch on email.
Yeah. Yeah.
Tapio is a Theodore Bai Wu Professor of Environmental Science and Engineering at Caltech. He's also a senior research scientist at the Jet Propulsion Laboratory, again in Caltech. He's a leading expert on impact of turbulent dynamics of the atmosphere on Earth's climate and has been recognized through numerous awards and grants. Um, for our purposes, I'll just focus on the fact that he heads the Climate Modeling Alliance, and that comprises, he'll tell us more, but that comprises about 70 researchers that is building a new Earth system model that uses the latest techniques from statistics, applied mathematics, and machine learning, and diverse available data with the aim to develop accurate and precise climate predictions. So it's very exciting work, and certainly it fits it with the purpose of this event, where we are getting introduced to the developments in climate science and exciting new developments in climate science with a view to something that we can maybe hope to do in future in India. So Tapio, please go ahead.
Yeah, thanks for having me, and pleasure to be with you virtually. One challenge with these virtual meetings is always to, well, read the audience and make it interactive. I should say from the outset, I like being interrupted. If there are questions coming up, speak up in the middle, and I'll try to have a look at the chat too. If there's anything in between, put things in the chat. And I think I want to emphasize our approach and how we use machine learning tools to improve climate models. And experience has shown, I mean, our approach is quite different from what anyone else is doing in that regard. And it sometimes takes a bit to assimilate the approach, I suppose. So please do ask questions when they come up. So I'll talk about our approach, and our approach is that of CLIMA, the Climate Modeling Alliance. Many people have contributed to what I'll show you, and I'll try to mention a few of them as I go. First, the why question, I think, doesn't need to be belabored here, but it is clear that climate is changing. Thanks to the work of Suki Manabe and many others, we know that mitigation is essential. But beyond mitigation, you could argue we know enough about the climate science to know that we need to mitigate climate changes. But where there are still large scientific gaps is having the information you need to adapt to the climate changes that are coming, that are underway. Various ways of looking at it. You can look at damages from climate-related disasters. In the US alone, they are reaching something like 250 billion annually. Worldwide, there were United Nations reports that were estimating damages will reach hundreds of billions in a few decades. In fact, we are already there. Not all of these damages are directly caused by climate change. There are other factors playing a role, more people living in coastal areas and the like, but there is a substantial component due to climate change in flood damage, for example, that's already manifest, and we need to adapt to it. We need to plan infrastructure that can absorb the climate risks we are facing, and we do not have the information we need to adapt cost effectively and efficiently. Now, mitigation is essential, adaptation is unavoidable, and there is a large economic case to be made for adaptation measures that tend to be very cost effective simply because the benefit cost ratio is enormous. For example, strengthening early warning systems. In India, early warning for floods, for example, can save a lot of lives, and adaptation measures there are estimated to have benefit cost ratios of somewhere between a few to 1 to 10 to 1 or so. So the strengthening early warning system, it's perhaps closer to 10 to 1. Water resource management, it's perhaps somewhere around 4 to 1. Either way, investing now is paying off in the future is the bottom line of it. This is from a Global Commission on Adaptation report 2 years ago. They were recommending investments in the $1 trillion range now to adapt to climate change. And clearly what we need to do so is knowing what to adapt to. And I think that's where we are still lacking the knowledge we really would like to have. If you reduce the problem to a cartoon, you could view it in this way, that on the one hand, we have an enormous amount of climate data from space, from the ground, from autonomous floats, gliders in the ocean and the like. It's of the order of magnitude a terabyte of data per day we are receiving about the Earth climate system. Those data are used to evaluate climate models, to hold the climate models next to the data to see how good or bad it is. But what has not happened to the degree it could happen is use the data to directly inform the climate model. So there's a piece of a pipeline from data to models that is broken or has never really existed for good reasons, and I'll explain why it hasn't existed. And if you want what we do as climate scientists to be used, we probably need to do more than write a 4,000-page IPCC report and hope that people will read it. We need to reach people who need to make decisions about stormwater management infrastructure, or say about development in the Ganges River Delta. Where do you want to continue to build and how? We need to reach people who make those decisions in ways that they can use the information, that their climate information is just only one piece of what they need. There's many other factors, obviously, always playing a role. So I think the other thing we need is better decision support tools, and to help the translation from what a climate model does to what people actually need. And your workshop is about AI tools, machine learning. Machine learning can play a role in all of this. I'll focus more on the learning from data part. For the discussion, perhaps we could talk about where machine learning can play a role on the decision support side. For example, the question that already came with respect to how can you use machine learning to say something about extremes. It's something we're working on. It's not part of a talk, but I'd be happy to discuss later on. So we do not have the accurate local information that we need for proactive adaptation. And I think it's clear to all of you what the problems are. Even global projections are highly uncertain, mostly because of uncertainties in models once you look at timescales of a few decades. And local projections are even more difficult, and the climate information needs are not currently met. There's a statement from the US Government Accountability Office from a few years ago. I think this has become even more acute since then. And the key problem in climate modeling in general are small-scale processes. It's processes that are too small to be globally resolvable, yet are important for climate. The suspect number one here is always clouds. Clouds are small scale, too small to be resolvable in climate models, so we need to do something to represent them parametrically. And about half the spread in the climate sensitivity that you see here in CMIP6 models comes simply from differences in how clouds are represented in these models. If you want to reduce it to one factor, you could say that the climate models that are more sensitive with respect to increases in CO2, that produce a larger global mean temperature increase in response to a doubling of CO2 concentration, which is what's plotted here, tend to produce fewer low clouds, especially in the tropics, than the models that have a lower climate sensitivity produce less warming in response to increases in CO2 concentrations. Reduced to one-dimensional variable here, you could say that the models have lower climate sensitivity, tend to produce more low clouds, reflecting more sunlight as the climate warms. The ones that are more sensitive produce fewer low clouds. There are other cloud factors that play a role. Microphysics, especially in mixed phase clouds, is also playing a role. And these are sort of the key uncertainties we have in climate prediction. This is for the global mean temperature in equilibrium, but the uncertainties in the global mean temperature map down into any climate impact you would want to consider. If you're asking about how much will the monsoon over India change in response to climate change, and if you stratify this across climate models, it stratifies along the equilibrium climate sensitivity axis quite well. Precipitation extremes are to a large degree controlled by global mean temperature changes. So any local impact you want to look at, the global part you have to get right first. The low clouds I'm talking about here, and I want to talk a bit more about later on, are low clouds over tropical oceans, especially, or subtropical oceans. So I'm sitting in the, can't see my mouse, so you can't see it either, but I'm sitting in the upper left quadrant of the left plot in California. There's a stratocumulus deck off the coast of California, Baja California. That's there pretty much year round. It's just a white blanket over the oceans reflecting sunlight. And if you go westward from where I am, you eventually reach the Hawaiian Islands, southwestward, and you see there is a cumulus clouds are much more prevalent, as dark ocean surface exposed, as a result of which ocean waters there are a good bit warmer than off the coast of California, or same is true off the coast of west coast of Australia or Angola or Namibia. In general, stratocumulus clouds are prevalent over eastern subtropical ocean basins, cumulus clouds more over the more central or western portions of the tropical or subtropical ocean basins. And the key uncertainty, the largest contributor to uncertainties or to spread among climate models, is that different models produce different responses of these low clouds to global warming. And in fact, all models have severe biases in their representation. All models underestimate the prevalence of stratocumulus clouds, for example, often severely by factors of 2 or 3. It's not a subtle bias at all. Clouds are one example of small-scale processes. There are many others. Ocean turbulence. In some ways, I would view the biosphere also as an example of small-scale processes. At the molecular level, we can model a lot there, but to course going into global scale, we have difficulties. And just to maybe emphasize one point a bit more than might be necessary, but because it has, I think, led to a lot of confusion, I want to make this very clear. The clouds we're talking about, as one example, have dynamical scales of meters to tens of meters. The climate model right now routinely has resolutions in the 100-kilometer range horizontally, going towards tens of kilometers. We have seen some simulations at around the kilometer resolution run for a brief period. But the essential point is that the dynamical scales of these clouds are orders of magnitude smaller than the highest resolution we can possibly achieve right now. And it's even truer if you consider the scales of droplet formation and the like, which is at yet smaller scales. So let's get this one point out of the way. You might ask, should we just build one big climate modeling center that builds the highest resolution models we can? Will that solve the problem? The short answer is no, and the slightly longer answer quantitatively is that if you plot the performance of the world's fastest computer since the Cherney report in 1979 to, well, we published this in 2017, so this is when the data here stopped. On the log axis on the right, these are gigaflops, computer performance in gigaflops, logarithmically plotted, and you see this truly flabbergasting continued exponential increase in computer performance, doubling roughly every 1.2 years. And despite the end of Moore's law, and despite the end of Dennard scaling, you're still at exponential doubling because of massive parallelism. Now that's reasonably well known. At the bottom, AR1 to 5 is the release dates of the IPCC reports, and they're there because what I overlaid here were all climate models published until 2017, and I published this figure from the time of the Cherney report. And what is plotted for the climate models is the horizontal resolution of their atmosphere models. And it's plotted in a very specific way, namely such that a factor 10 increase in resolution on the left axis exactly corresponds to a factor 10 to the 4 increase in performance on the right axis. And that is chosen this way because if you want to increase the resolution of a three-dimensional fluid isotropically by a factor 10, you need 10 to the 4 times as many flops, 10 to the 3 for space, and another factor 10 for time. And so the horizontal resolution we're looking at is starting at around 1,000 kilometers in Manawi's time early on the left. And we are reaching now 25 kilometers or so. And we are approaching the gray zone for deep convection. That's the horizontal resolution range between 1 kilometer and 10 kilometers. So that will become routinely possible within a few years. If you, perhaps rather implausibly, assume that computer performance will continue to double every 1.2 years. And you can ask, when can we resolve these low clouds that really are the crux of the matter? Just the dynamics of the low cloud. So let's just say we reach 10-meter scale resolution. Well, the answer is it doesn't even fit on the plot. It is somewhere to the far right here. If you extrapolate this out, you would be able to resolve the clouds by 2060. So what we need, and you can quibble about details of the numbers, but we need roughly a factor 10 to 11 increase in floating point performance of computers to resolve these low clouds. And different assumptions of how you distribute the resolution increase in a vertical versus horizontal and the like, you maybe get this down to a factor 10 to the 10 or 10 to the 9, but no matter how you parcel it, this is far out, not achievable anytime soon. And that's just to get to the dynamics. Even if you can resolve the dynamics, you're still not done with the microphysics of the clouds, the microphysics of droplets formation, ice crystal formation, and the like. So it's a beautiful graph from a terrific review by Morrison et al. It came out in James just a year and a half ago. And the crux of the matter here is that what a climate model provides are large-scale variables like humidity and temperature on scales of the climate model grid, so tens of kilometers on the side. And what we need are things like the cloud albedo, cloud cover, precipitation, and the like. And to translate from humidity, temperature, to the variables we actually need, we need to, in some fashion, bridge all these scales here that involve this myriad of small-scale processes. And with brute force computing, there's no way. We can simulate microphysics accurately, very accurately, and it's great fun to do. You need to resolve the Kolmogorov scale of turbulence, and you can do it in volumes, a few cubic centimeters on the side, nothing close to the globe. So this figure, by the way, is from a paper in Physics Today that Nadia Giovanni, Rob Sokolow, and I wrote. It came out last summer that in more general term outlines the approach I will be sketching here. So clearly, we all have admired the advances coming from AI tools in various fields, from playing games to now really solving the protein folding problem, which is truly impressive. And in some ways, these tools have to play a role in the climate problem too. And as I said, we have data. We have high performance computing capabilities that are stunning. I mean, the computers we use now are already a factor 10 to the 8 faster than what Suki Manabe used early on. Without climate models having gotten a factor 10 to the 8 better, I would say, however we would measure that. But climate is quite special and has very different needs from, say, AI tools you might use for weather prediction. And I want to talk about these special requirements and why they matter. And let me just say one thing. I can't see my mouse, as a result of which I can't open the chat. Let me just exit full screen for just 1 second, because I see there's something in the chat that I would like to be able to see. Okay. Go back to full screen now that I can see if there are questions coming up. Oh, right, there was a question. Last 30 to 40 years of CO2 increase. Does that tell us how clouds change with it? Yeah, you wish. The problem is we don't have good data for clouds for a long time. We have detailed satellite observations for clouds only for the last 15 years or so. And before that, we have scattered observations, say ship-based observations that it's really hard to extract trends from it. There's a lot of natural variability and people have tried. I mean, there is some suggestions that, for example, these low clouds have thinned, but it's pretty tenuous, the empirical evidence there so far. So the data we have, there is lots of fantastic data we have. For example, I will mostly talk about the physical aspects of the climate system clouds, but one thing I've been quite fascinated with and involved in modeling is also Earth land surface and biosphere especially. When plants photosynthesize, they give off some extra energy so as not to overheat as infrared photons. And that's known as solar-induced chlorophyll fluorescence. And it's a very faint infrared glow of plants. And that is approximately proportional to the rate of photosynthesis, primary productivity. And amazingly, Christian Frankenberg, one of my colleagues at Caltech, figured out how to measure this from space. So this is from the Tropomi satellite, solar-induced chlorophyll fluorescence measured over a year. And we can see Earth breathe from space, literally, for the first time. So the one other big uncertainty in longer-term climate predictions is what happens to the carbon cycle. And for the first time, we can see photosynthesis, or a good proxy of photosynthesis globally, which allows us to separate photosynthesis from respiration. And it's really game-changing for how we model the land surface. Come back to that at the very end, just give one example of what we are doing with this. Then, of course, cloud data. We have now Cloud Radar, Cloud LiDAR for roughly 15 years. So typically polar orbiting satellites, CloudSat Calypso, polar orbiting. They provide global coverage of various aspects of clouds. The temporal resolution is low. It's a polar orbiting. You go over the same spot on Earth every 2 weeks or so, but it's global coverage spatially. So it's data we should use. This data is somewhat underused. It's not even assimilated typically in weather forecasts because cloud cover is a very rough statistic. It makes a big difference whether a cloud is in one spot or a few kilometers away. It makes it a challenging task even for a weather forecasting model to assimilate this information, and directly using this information for climate models is even harder. But we have those data and we ought to use it. And the other source of data, of course, is data we can generate computationally. Here's a large eddy simulation of Caribbean cumulus clouds we did. Gray is a cloud, blue is rain, the colors on the surface is buoyancy, or more or less temperature. So this is resolution done at about 10 meters, simulation done at about 10 meters resolution. And we know these to be very good simulations. We can compare them with field data, and we know what approximations we're making here numerically. We can control them. So these are good simulations of the cloud dynamics, the turbulent dynamics. Microphysics, droplet formation and the like, is still parameterized. We still cannot resolve it. So all of that is still uncertain. But the dynamics is well represented. It's just solving Newton's laws and the laws of thermodynamics of finite grid. Of course, you can't do it globally. That was the point of the earlier slide. But you can do it in patches, a few kilometers on the side. I think the magic point right now is that the domain size that's feasible with these simulations is just about the footprint of a climate model grid box, so tens of kilometers on the side or so. So we have lots of data observationally, we have data we can generate computationally, and we want to use all those data to learn about the climate system and to make climate models better. And now here's the crux about the contrast to the weather problem. Why this problem is a lot harder for climate than it is for weather. For weather, you can say if the problem is mapping an initial condition to a condition of the state a week later or a few days later to produce a weather forecast, you'd be happy with a black box model that does that well. As long as you can just check every day, it still does it well. Probably most people will be satisfied. It doesn't need to generalize much out of the observed sample. It's just you can train it on enough weather data. Generalizability isn't essential. All of that is really fundamentally different for climate. We need to predict the climate that has no observed analog, so we cannot train it on climate data that we simply don't have. You could train it on simulations, but then what you're building is an emulator of another climate model, but not using the ground truth. If you want to use observational data, you need to generalize out of the observed sample. I would argue that interpretability is absolutely essential for climate models, because in the end, we're asking the public to trust what we put out there. And one ingredient for that trust is that what we do should be scrutinizable from beginning to end. You need to be able to take this apart to see, how did you arrive at your inference here? What went in from data to the model? And I think a lot of us would be pretty skeptical trusting some black box model with 1 million parameters that happens to fit the present climate well, but if we can't interpret it, we would be skeptical whether that gives us a good climate forecast. And one thing that we have learned from weather forecasting is that uncertainty quantification is important. We need more than just a point forecast. We need probability forecast, risks forecasts, and sense uncertainty quantification is important. And well, I would say these 3 requirements are essential. You can ask, how do you meet them? Let's think for a sec about deep learning. Deep learning has been enormously successful it has been enormously successful by ingesting large amounts of data. The models that have been so successful have been successful because they're very expressive, but very expressive means they need a lot of data. In essence, the success rests on over-parameterization of the problems. And that works great in many areas. That works great in areas where you're very data rich for classification problems, distinguishing cats from dogs and the like. All of that can be enormously successful. But generalizability is always an issue with these methods because in some ways you're overfitting, or you can try to guard against the overfitting, but you over-parameterize. Generalizability is always a challenge. Interpretability is a challenge for the same reason. If you have a complicated, highly nonlinear model with millions or even billions of parameters, interpretability becomes a real challenge. UQ becomes nearly impossible in that case. At the other end of the spectrum, we have science as we have practiced it for the last 400 years or so, since Bacon's time. It's called reductionist science. It rests, by contrast, on parametric sparsity. Think about Newton's law of universal gravitation. It's a one-parameter law that is good for modeling apples falling from trees or for planets orbiting stars. It's extremely generalizable, it's extremely interpretable, and it is our model of how science should work. Now, the challenge, of course, is that an equivalent model to Newton's law of universal gravitation for clouds we would all love to have, but we haven't succeeded in inferring, and we probably will not succeed. Systems as complex as the Earth system or just a turbulent system alone, they're probably not amenable to the reductionist approach to the end. But I would say it's not either or, but both that can lead to success here, and combining the best of both worlds. And I try to explain how we do it and with a few examples. But let me just contrast it before I go into how we do it with a lot of work in the last few years that I think has been really interesting and illuminating work, but that I do not think will lead to a satisfaction of these three criteria outlined: generalizability, uncertainty quantification, and interpretability. Pretty much all machine learning in the climate sciences so far was a variant or another of supervised learning, which means that, so here's an example from a nice paper with Pierre Gentil and collaborators. You take data, in this case, the data are in the right column, produced by higher resolution simulations, super parameterized CAM in this case. And these data produce the trajectory, convective heating rates, convective moistening rates, short-term tendencies. And you can learn an emulator for these tendencies, given the state of the simulated atmosphere, given temperature, humidity, all the other variables, right? And you can do this quite successfully. In this particular case, there's about 1 million parameters being fitted in what is a fairly simple, still fairly simple climate setup. And it works successfully in that you get a good emulation of in this case, the super parameterized CAM. So you get a good convection parameterization with about 1 million parameters. What it doesn't do well is generalize out of the sample. These approaches tend not to work very well if you then try to simulate a warmer climate and compare it with the simulations. And they're definitely hard to interpret. There are also stability problems with it typically that leads to a lot of manual tweaking that's necessary to, say, put this machine learning emulator actually in a climate model and run it forward in time. Oh, isn't overfitting the same as overparameterization? No, I wouldn't say so. Overfitting is really when you overfit. I mean, you're too close to the data, and you can guard against that with, there's a large literature in the machine learning world. You guard against it with variants of cross-validation and the like, regularization methods. Overparameterization just means you use a very expressive model with a large number of parameters, perhaps larger than you minimally would need for a scientific description. I mean, here's, I think, a good example. This is essentially, the left column is a convection scheme and it has 1 million parameters. Probably most of us would prefer a convection scheme with fewer parameters.
I have a naive question. So you said that you cannot generalize what you learned from this to warmer clouds. Is that what you said?
Yeah, so unless you train it with warmer climates, it will not predict the warmer climates well. That's sort of a general message of these types of approaches.
Okay, so is there anything else about warmer climates that makes it harder?
No, I think it's just being presented with a warmer climate in a training phase. You can ameliorate the problem a bit by, Mike Pritchard has been doing this recently by, for example, learning these tendencies in terms of non-dimensional groups rather than dimensional humidities and temperatures. But the fundamental problem is these tools have a hard time predicting something they haven't seen in a training sample.
Thank you.
And but let me maybe say one more word. So suppose we figure out a way of doing that. I mean, generalization is a big topic in machine learning, and people think hard about how to do this. The other problem with the approach is that this is learning from trajectories or tendencies. We do not have them from observations. You can generate them computationally, you can get them from a reanalysis model maybe, but you get them from a model, not from data. And I think that's another fundamental limitation of this type of approach. It's worth doing, and I'm glad. I mean, I'm working, for example, with Pierre Gentil and other aspects. I mean, this is all. I don't want to give the impression that I do not value the work. I do. I just want to make the limitations and the contrast to what we do clear, because I think my experience is it's sometimes it's hard to see the differences. So our approach is really the best of all worlds here. Bring theory forward, meaning use the equations of motion where you have them and what you know about the processes. Use it as much as you can. For example, with systematic coarse graining for turbulent approaches, the key here is to promote parametric sparsity. And in other words, the more you use of what we know about the system, the less you need to learn from data, the less you put the onus on data to inform what you do. We want to use data as massively as we can. So we want to exploit Earth observations. That was the premise for our whole approach, together with data generated computationally, which is in some ways is easier to work with and easier to get. And computing power is also important. I mean, brute force computing isn't going to solve it, but we shouldn't ignore what we can do with brute force computing. And the transition to hardware with accelerators is a challenge in many ways. We need to rewrite a lot of climate models to use these architectures, but it's also an opportunity to rethink how we use what computing architectures we have now. For example, we can now do distributed local simulations of small scale processes, clouds or sea ice or ocean turbulence. We can run them in a distributed fashion in many places. They do not need to communicate very much with one another. And we can very efficiently and effectively generate computational data that way. And it's a different use of the computing power than simply going to higher resolution everywhere, but it's a use that's well adapted to the form in which this computing power is presented to us. In reality, is climate modeling is not driving the hardware evolution. It's computer graphics, it's machine learning and the like, and we just need to piggyback on how the hardware is evolving rather than wishing for the perfect machine for fluid dynamic simulations. So in a cartoon, what we're doing is this: we are building a system that learns from observations, be it from space, from the ground, and from high resolution simulations that you can drive with a climate model. You can spin out of the climate model in many locations. These can be thousands of locations. It just can't be everywhere because everywhere is too computationally expensive. And we have generated a library of large eddy simulations that stands at a little of 400 simulations so far, going towards 500. And it should soon be in the thousands. And those simulations we use to train closure models that are embedded in physical laws. So here's as one example, illustratively given the Navier-Stokes equation, where it's a coarse grain and you get Reynolds stresses. These Reynolds stresses depend on variables on the grid that you have, and various non-dimensional groups ultimately that you can construct. And those closure functions is what we learned from data, be those data given by large eddy simulations, for example, or observations. And I'll show you an example with cloud modeling, how this actually works, and I think works quite well. So the key to our approach and how we started out was saying we want to learn from time average climate statistics rather than from tendencies. Tendencies we do not have observationally. Time average statistics we have. If polar orbiting satellites, they don't give much temporal resolution, but once you average in time, once you aggregate in time, we can get good statistics, for example, of cloud fields or sea surface height, quantities relevant for ocean observations and the like. And Sandeep is saying observations are more valuable than computationally generated data. I agree. How do you weigh the two? Let's come back to that question. That's actually a good one. We have a crude way of doing this right now that I'm not sure is the best way. But essentially, to say it briefly, we generate priors from large eddy simulations that then we update with observations. And there's a whole field of multi-fidelity data, multi-fidelity simulations that I think can be informative here. And I don't think the last word has been spoken on how to do this well. So learning from statistics, there are several reasons why this is a good idea. A, it focuses directly on what matters for climate prediction. Climate statistics is ultimately what we want to predict. Statistics here are not just mean fields. These can be higher order statistics, covariances. They can be extremes. They can be any higher order statistic you can dream of. And covariances, I think, are a particularly good example. We have a large literature on emergent constraints, which are essentially fluctuation dissipation relations of one form or another, that says that the covariation, say, between SST and cloud cover now over a seasonal or interannual variability is predictive of the response of the system to perturbations. And by building in covariances of that type in your loss function, you can directly build in an emergent constraint as something you learn from rather than something you use to evaluate a model with. And the key thing is the learning here is treated as an inverse problem rather than a supervised learning. And it doesn't come for free at all. There are severe downsides. One is simply averaging destroys information, and it becomes a question of how do you average judiciously that you keep information that's relevant without throwing away interesting information. So a simple thing is the seasonal cycle is very informative about the climate response. You don't want to average over longer timescales than that, because otherwise you throw the seasonal cycle out and you throw out a lot of valuable information. And the most severe downside, and why I think this hasn't been tried before very much, is that the loss function evaluation is extremely expensive. You need to run the climate model for seasons or longer. And typically standard learning approaches for inverse problems, Bayesian learning approaches would require 10 to the 5, 10 to the 6 loss function evaluations. That's just not doable with a climate model. So the seasonal cycle is just one example of what is informative here. You can pick a seasonal cycle in many quantities. Here's just an example for sea ice. This is from the CMIP 5 models. Arctic sea ice extent seasonal cycle. The colors are the models, and black are observations, and the arrows indicate roughly what the expected global warming response of sea ice will be to increases in CO2 in the next few decades. And the essential point is that the variations in, say, the amplitude of the seasonal cycle between models are much larger than the climate response. So the biases in the models are larger than what we want to predict, which should be uncomfortable to begin with. But it's an opportunity because it allows you to use these mismatches to try to improve the models. The models are colored from yellow to red in order of increasing climate sensitivity. So what's interesting here is that there seems to be a correlation between the climate sensitivity a model simulates and the amplitude of the seasonal cycle, the mean state in the Arctic. So this is saying the seasonal cycle is probably informative about the climate response of the model. So do the seasonal cycle better, probably you also get a more predictive model. It's not a guarantee, but at least it's a suggestion. So let me talk about a few aspects of how to learn from this data, how to solve this inverse problem, and then give you some concrete examples on how we use all of that inside a climate model. So the crux with the difficulty with the approach is In fact, Balaji, who just spoke, I think I asked him before we started with, how many times did you run the GFDL model to calibrate it by hand for the latest iteration? And Balaji, I think, gave me some numbers, somewhere in the 700, 800 or so. And there were some debug runs, and not all of that was tweaking parameters by hand. But what I took from it was that you can run a climate model around 1,000 times. That's something that's very affordable. And if you automate it, it's even more affordable than if you do it by hand. So the task we gave ourselves is, how can we learn from data, from climate statistics, but only running a model roughly 1,000 times? And here's what we came up with that works very well and works better than we thought when we came up with it. It's an algorithm we call calibrate, emulate, sample. The problem we're trying to solve is this. We're given data Y, and we're giving a climate model that maps from parameters theta to the climate model's version of data. So G of theta is the mapping from parameters in the model to climate statistics. And I should say the parameters can be standard parameters that, as we are used to. They can be weights and biases in neural networks. We've done that now. They can be hyperparameters in non-parametric models, Gaussian processes. The parameters are to be understood broadly. I think Balaji mentioned dictionary learning approaches where you learn differential equation terms from a dictionary of differential equation terms. That would also be subsumed in this formulation. The mapping from parameters to the model's version of the statistics, G of theta, is a noisy mapping. There's internal chaotic variability. You're looking at finite time averages of the climate model, as a result of which there needs to be a noise term eta, but this noise term, by central limit theorem arguments, should be reasonably Gaussian simply because we're looking at averages. Now, we also need to assume that it has zero mean, which it generally, of course, does not. The way to achieve a zero mean is by including structural error models inside this mapping G of theta, which is likewise something I'd be happy to say for the discussions on how we do it. We're just finishing up a paper on various approaches on how to include structural model errors in this approach. Now, what the CES algorithm does is calibrate the model, which means solve an optimization problem that gives you approximately good parameters theta by solving this inverse problem. And you can use variants of common inversion here very effectively. We started out with ensemble common inversion, which scales well to very high dimensional problems. We use it in weather forecast with problems of dimensionality 10 to the 9. The way to think of what this calibration step does is that it generates pairs of parameters theta and simulated data Y that are placed in the parameter space that can be high dimensional in such a way as to sample the posterior effectively. It common inversion, ensemble common inversion, and its variant will place points, or pairs, theta and Y, near the posterior maximum. Common inversion is extremely good at finding that maximum. The problem is that it tends to collapse. The ensembles tend to collapse. And as a result, it's not good at uncertainty quantification. So typically you need order 100 ensemble members. We have since worked on other algorithms, for example, scented common inversion, which needs smaller ensembles, so the parameter space is smaller. There's something called the ensemble common sampler that avoids the collapse of the models. But what all of these methods have in common is that you need order 10 to 100 ensemble members, and they converge over a few iterations. So, typically ensemble size 100, 5 iterations, you have 500 evaluations of your climate model. So that's doable. Or 10 iterations, 1,000 iterations, 1,000 evaluations. So that's what we started out with. So then you have 1,000 pairs, theta and Y. And what you now can do to do Bayesian learning is train an emulator on these pairs. And crucially, what we're emulating is the climate model statistics, not the entire model. You're not trying to emulate every rainstorm. It's just the statistics that we consider to be informative, precipitation statistics, for example, the mapping from parameters to these precipitation statistics. And for the emulator, you can run the gamut of machine learning tools. We started doing this with Gaussian processes. We have since done this with neural networks. We have done it with random feature models. We have now done it with Fourier neural operators. Any number of approaches can work for emulating this mapping. And the key thing is that evaluating whatever mapping you learn is very cheap computationally. It's essentially free relative to the running the forward model. So you can sample from this emulator, can sample 1 million times if you like with Markov chain Monte Carlo, and what you get out is posterior densities over the parameters. The algorithm, the whole idea originated working with Andrew Stewart, who was a key contributor here, that we were sitting in a room and thinking we have common inversion, and then we typically just look at the last iteration of common inversion and the ensemble is collapsed, and we lament the fact that it's collapsed. And there was this moment said, wait a minute, we have all these other forward model evaluations. Why don't we use them too and emulate them? And this is what came out. I think what at the time we didn't realize fully is how well this works in the presence of noise. It's extremely robust with respect to chaotic variability that otherwise is a real challenge for, say, MCMC getting stuck in noise-induced minima. And Andrew since has written papers on proving that it's robust with respect to noise and the like. It at first was an empirical thing that became clear to us as we experimented with it.
Sorry, a quick
yeah.
So this, I guess, this update of posterior density, are you imagining this to be part of the Earth system model being done online, or is this going to be done offline?
I'm maybe not entirely clear what the online-offline distinction is here. So what you would need to do is that you take your Earth system model. Ideally, you do this for all components jointly. You get joint densities. And in a computationally very intense training phase, where you need your 1,000 evaluations of the model, you are generating this posterior. And once you are given the posterior, you can draw from it and generate climate predictions that will sample the uncertainty space as given by this posterior that's data constrained. Not sure that answers the question. I was just trying to parse the online-offline distinction.
Will this be done many, many times in your Earth system model, or just a few times?
Okay. So I think there are two aspects to learning here. There is okay, maybe I get it now. They're the computationally generated data. Those you can generate in any climate you simulate, in a warmer climate as well. And there you can use active learning, online learning approaches to keep updating your parameters. And the Earth observations we have, well, we have them for a given period. You train with them once and perhaps retrain when a few more data become available. So that would be offline. You can make this process online with the computationally generated data. I don't think you would want to do this too many times. I mean, you probably run this out in the future and make sure that things remain stable and the parameter estimates don't change vastly. And we have so far only done this in an offline setting. I'll show you an example of how we have done this offline, but that part you could do online.
Thanks.
I have an example here of how the algorithm works, and perhaps in the interest of time, let me just skip the details of it, because I want to talk about the cloud modeling. And just a brief example from a biosphere in the end. Let me just run through it very briefly. This is just a two-dimensional, very simple example. The simple convection scheme and an idealized GCM. It's just a proof of concept. And for those who want to know more, maybe the link at the bottom has a paper that has the details. But let me just say only one thing, perhaps briefly. So here's this common ensemble in a two-dimensional parameter space, collapses to the point. You know what the point is. This is a perfect model experiment over 5 iterations. But I just want to say what we're emulating and what the loss function is. The loss function that went in here, excuse me, in this particular case is pretty simple. It contains the relative humidity in a mid-troposphere. It contains the mean precipitation rate as a function of latitude. This is an aquaplanet model, so it's statistically axisymmetric. So we only need to look at functions of latitude, much simpler than the real world or a complex model. And this was one example. We also used one statistic quantifying intense precipitation. The statistic here is the frequency with which the 90th percentile of precipitation in a control simulation is exceeded. So if you have the right parameters, that should be exceeded 10% of the time. What you see in blue is the climate model run many times with the whiskers indicating internal variability, 90% confidence intervals. And in orange is the emulator. So maybe that's just the only point I want to emphasize. What we're emulating here is the terms in a loss function, which are in this particular case, 3 statistics, function of latitude, and the emulator captures the mean and the variability of those statistics extremely well. This is for a Gaussian process. They don't scale too well to high dimensional spaces. As I said, we haven't since done this with other emulators that scale better to high dimensional spaces. Then you have an emulator. You can sample the emulator, do Markov chain Monte Carlo, in this case 500,000 iterations, and you get the posterior density out of it. In this case, this 2-dimensional parameter space. These are parameters in a convection scheme, and I didn't really say what they are. It's a relative humidity and timescale parameter. The point is you get a posterior density that, in this case, is simple enough we can verify is a good estimate of the uncertainty. We can prove that in a linear case. It's harder to prove anything in a nonlinear case, but we can show computationally that by brute force sampling of this GCM, in this case, it's easy enough to run thousands of times. We can verify this is actually a good representation of the posterior density. This is a simple example. It's a fairly Gaussian posterior density after the variables were transformed. They are not Gaussian in the original spaces. We just transform to spaces in which they're plausibly Gaussian, like the relative humidity. We transform from uniform to a distribution on the real axis. And in more complex cases, you get all types of complex behavior, ridges in the posterior density, indicating correlated parameters and the like. The point is you get something out that is easy to interpret, can induce you to go back to whatever you were estimating, especially if you have correlated parameters, to see if you can make them more uncorrelated by revising the model, for example. You get a posterior density, you can draw from the posterior density and now do any number of climate change predictions. So you have the posterior density on these parameters, and this was unbiased by construction. The problem gets a good bit more complicated when you need to include structural model errors. And there's a few preprints on our web page. And as I said, the paper that I need to finish as soon as I can, that lays out the structural error models in more detail. It all goes back to work that Jinlong Wu was leading, and it's just on my desk to finish that part. So you can draw from the posterior density, then say increase the CO2 concentration in this pretty idealized climate model and look at predictions. So here is an example of a prediction of a precipitation extreme. Now this is truly more extreme. So we looked at the 99.9th percentile of control precipitation at each latitude, of precipitation in the control simulation at each latitude, and ask how often is that former 99.9th percentile exceeded in a warmer climate. And you see the exceedance probability here reaches 1 to 3% in the exotropics of what used to be a 0.1% probability event. So you see what we know, that extreme precipitation gets more frequent by this metric, especially in the exotropics. But even more interestingly, that we can now look at uncertainty. So the orange band is from an ensemble drawn from the posterior I showed you before, ensemble of size 100, integrated forward in time, and now just drawing 90% confidence intervals on this point estimate of the precipitation change. And what it does is, well, in this case, it does what we kind of knew, that in the exotropics, for example, extreme precipitation changes are a good bit less uncertain, definitely in this idealized model, than in the tropics, where the range is quite wide. In the tropics, convection dominates what dominates the precipitation response, extreme precipitation. In the exotropics, it's still convection, but it's organized by large scales, and the uncertainties as a result of which are much smaller. And it's just a prototype example of what you can do with this approach with a real climate model. What we're doing is building this real climate model, and I wish I could show you the same results for now a full-blown climate model. And by the end of the year, I hope I can show those results. So right now at Klima, what we're doing is build this Earth system model. And we spent the last few years, an enormous fraction of our time, on this developing the physical, biological, chemical components of this model. And they are familiar to all of you. I mean, there is nothing too radical about most of those aspects. A standard dynamical core, a standard ocean model. It's nice, it's all new software, it runs on GPUs and the like, but in essence, it looks like where system models look elsewhere in many important respects. There are important differences I'll describe. And so the idea is to wrap a data assimilation machine learning layer of the type I just described in the end around all components jointly and inform them both from observations and computationally generated data. And I think it was Sandeep who asked before, how do you combine these two data? So right now the approach is use computationally generated priors for the observational data. And I think there's probably better ways of doing it, and we haven't quite figured all of that out yet. So let me just give you an example from modeling clouds. Just to make this a bit more concrete, and mostly giving that example because, well, that's the core of what I do. There are many others working on other aspects. Say, the MIT group has used very similar approaches for ocean turbulence, and to my surprise, you can use similar approaches for land biosphere. I'll just show you an example in the end. So you start with the equations of motion. It's just somewhat symbolically written here as a continuity equation and an equation for some scalar phi, where that scalar can be a velocity or can be a thermodynamic variable or moisture variable, whatever you like. And what we do is we coarse grain the fluids equation by conditionally averaging the flow domain within a climate model grid box over n subdomains, or n plus 1 subdomains, I should say, where these subdomains label coherent structures, updrafts, downdrafts, and a distinguished subdomain indexed by L equals 0 here, I equals 0 it should be, that we call the environment that's more isotropically turbulent. So these ideas go back to pioneering work at ECMWF a good 20 years ago. Pierre Chebyshev, Jal Teixeira, and others were leading that, coming up with what they called the eddy diffusion mass flux prioritization. We are following their lead here with some extensions, but the basic ideas are theirs. And you do this conditional averaging over the subdomains, and what is written here on the left-hand side are your standard terms in any conservation law. What you acquire is this term AI, which is the area fraction occupied by subdomain I, but otherwise it's the standard continuity equation on the left-hand side. So it becomes an equation ultimately predicting the area fraction. But again, you average, you lose information, and that information loss shows up on what's written on the right-hand side as interaction terms between the subdomains, updrafts, downdrafts, environment. They interact through entrainment, detrainment. Similar approaches, I should say, are also being worked on by John Thuber and Hilary Weller in the UK. Called it a multi-fluids approach. It's essentially the same approach, and I think very complementary and pursuing similar ideas. For scalar mean, any scalar, you acquire some additional terms. There's entrainment, detrainment of the scalar, then there are turbulent transport terms. And I don't want to spend time on how we close those right now, just to say that everything on the left-hand side are terms that you can put in a dynamical core of a model. And everything on the right-hand side, we don't know a whole lot about. But we do know a few things, say entrainment, detrainment, mass exchange between a cloud and its environment. We do not know how to model this with precision. We know some limits of that should obey. We know entrainment epsilon ij is entrainment from the subdomain j into I. Well, that should be equal and opposite to the corresponding detrainment terms. So there's some symmetries we know. These functions should be positive, we know. That's about it. So these are closure functions. Well, maybe they aren't even functions, they could be functionals. But they're really good targets for learning from data. This is where machine learning comes in for us. What we started out doing, and these papers referenced at the bottom, is guessing functions. And it was several years of fairly hard work of trying to come up with good guesses that seem stable and that work. And somewhat frustrating work, perhaps I should add. I mean, Yair Cohen was leading a lot of that together with Ignacio Lopez Gomez. Part of it because there's little theory to guide you, can be hard. Ignacio did really pioneering work on first principle derivations of what mixing length in this formulation should look like. That was really physics rooted and extremely successful. But say entrainment, detrainment, it's a good bit harder to come up with first principles saying what this is. So this is where machine learning is natural to use in these places. So we came up with our hand-tailored functions where there's a few parameters to fit, and published some papers on it. It works quite well. And what we now have done and are doing is replace those by stochastic functions, by neural networks, by random feature models. Nice thing is we have built a pipeline where you can just stick your favorite machine learning tool in there and just try out what works well and how it generalizes. Just in the interest of time, let me skip over a few things. We generated a library of large eddy simulations. The way we did it is by essentially driving a large eddy simulation with output from climate models, for example, from HGM2 and a few other climate models. Details aren't important. We did this as a bunch of CF sites, so sites where there is sufficient climate model output to look at cloud feedbacks, and generated a library of training data. And what we did is, at first, simply calibrating scalar parameters in our hand-guessed functions. It turned out to be 9 parameters that mattered here. It's pretty sparsely parameterized. Turbulence and convection closure. Calibrate those and then see how well this does in simulating various types of boundary layer convection situations. The map on your left is just for orientation. It's a map of biases in a climate model. Not important what it is. I was skipping over that map before. Just to say, in the upper right, you see a polar boundary layer. It's the Gabel's field campaign. And what's plotted are velocities, horizontal velocities, U and V. And solid line and all these plots that are to come is a large eddy simulation. Dashed dotted lines are our single column model, our one-dimensional model. And for those of you who have worked in this area, polar boundary layers, stable boundary layers are extremely challenging to simulate, even at high resolution. So solid line is our LES, the shading is a range of other LES, even those vary quite a bit. They're challenging to simulate even a large eddy simulation, in this case with about 2 million degrees of freedom, because they're so intermittent. And our one-dimensional model that has somewhere a bit from a few dozen to around 100 degrees of freedom, compared with 2 million for the LES, does essentially as well as the LES, provided the vertical resolution is high enough. High enough turns out to be, you need tens of meters resolution in the lower part of the atmosphere to get this right. Stratocumulus clouds is another example of something that's challenging to simulate even with LES, and that climate models struggle with. So in fact, the map on the left is bias in cloud cover in the climate model, and red means it's an underestimate of cloud cover by a factor of 2 or so for the saturated red regions. So lower right is the DICOMS field campaign measuring stratocumulus clouds from aircraft. Black is a large eddy simulation, again, our LES, which we think is quite good. Gray shading is a range of other LES, and blue is our parameterization, our 1D model. And again, the LES is order 2 million degrees of freedom. The blue line has order 60 degrees of freedom, and orange are aircraft observations at the site. We can reproduce the observations well, we can reproduce the LES well, and the key thing is it's with the same physical model as for the stable boundary layer, just the same parameters. It's a unified parameterization. You can also do shallow convection, maybe less exciting because it's not considered as hard a problem. Deep convection at the lower right, it's a bit more interesting. So this is vertical velocity in LES in deep convection over the Amazon, and our single column model below. And the key thing is that we get the smooth onset of deep convection at the phase of the diurnal cycle quite right. Crucial for that actually is something I didn't mention very much, is that in these parameterizations, we have memory terms. They're explicitly time-dependent terms for area fraction and the like, that give you continuous evolution, where, say, in typical climate models right now, you have switches from shallow to deep convection that essentially chop up the continuous spectrum of nature into discontinuities in models. It's just an animation showing that. So if you start looking at the right, it's vertical velocity heating from the bottom. Vertical velocity is starting you start forming a cloud in liquid QL on the far left that gradually rises, reaches the freezing level. You get ice, cloud ice in green. And once the cloud is deep enough, precipitation sets in the middle panel. And you see you have this very natural, smooth evolution from boundary layer turbulence to cumulus convection to ultimately deep convection. And we were very happy to see that this works within one physical framework for everything, boundary layer turbulence to deep convection. As I said, we are in the process of experimenting with how we can make these simulations yet better with this LES library we have. One thing that to me was extremely reassuring for the approach were results like this. We published first papers on the physical model 2 years ago. And of course, the concern is you show some case studies in those publications, and the worry is that we would have overfit to these few case studies we looked at. And once you look at new data, everything will fall apart. And fortunately, that wasn't the case. And you can show this rather explicitly. So for example, on the left is the mean squared error in training this model on large eddy simulations only for the present climate. And this is just calibrating these 9 parameters I mentioned. You see how the mean squared error over a loss function that includes things like liquid water path, vertical profiles of liquid water, and liquid potential temperature and the like. The errors are reduced by an order of magnitude relative to what I showed you before. And that's nice. And there are different common inversion algorithms you can use for that. Unscented is UKI and ensemble common inversion. Doesn't matter for our purposes how you do it. You get a fairly monotonic error reduction as the point. And what's even more interesting though is the right panel then. So for the same, you train this parameterization only on the present climate. And then we validated it with large eddy simulations where we increased surface temperature by 4 degrees. It's a reasonably large climate change. And evaluating the same mean squared error, but on the validation sample that was not part of the training sample, we see the same error reduction, which is to say, it really pays to use the physics as far as we have here, guaranteed energy conservation, mass conservation, all those things you like to have, and only learn the functions that in some ways we always have learned in fluid dynamics since Prandtl's time. So if you think of Money-Novikov similarity theory, they're in the end similarity functions we learn from data, and we're doing the same thing. You learn functions of non-dimensional parameters from the data we have, and that approach seems to generalize quite well, and that's quite heartening for all of us. We're in the process of figuring out how complex a model you want to stick, say, into entrainment, detrainment closures. We experimented with shallow neural networks that work as well as what I've shown you. They're probably underfitting, and we're just trying with the opposite limit of overfitting and then see where the optimum lies in the middle. And that's work in progress where we don't have all the answers yet. So we're pursuing the same approach for all components of this all newer system model. You could question why you do need something all new. Strictly speaking, you don't. You could do a lot of this with existing models. But the advantage of new models, aside from computational advantages, is that we made a large effort to reduce the parameter spaces as much as we can. So this convection turbulence parameterization has far fewer parameters than similar parameterizations in current models, and still it works better. And that was one opportunity that the all new aspect allowed us to exploit. And I think in the ocean, we have seen similar advantages, land as well. So need to put the pieces together. That's ongoing work. I hope we'll reach a completion that at least by summer, we have an atmosphere land model. The MIT group has done parallel work on the ocean model that's coming along well. Before we couple ocean, atmosphere, and land, that's pretty late this year or next year. But I hope by summer we can start learning from observations from space, in addition to the learning from high resolution simulations I've shown you. The algorithms are all in place. The work that remains to be done is largely integration work. Just one, perhaps a teaser, we have pursued similar approaches for the biosphere. It was led by Christian Frankenberg with Yuji Wang and a few others. As I said, there's solar-induced fluorescence data. which we can directly simulate. We built a land model that directly simulates that based on mechanistic models of photosynthesis and mechanistic models of roots and plant hydraulics and the like. And the top panel is our primary productivity that we simulate. The bottom panel is primary productivity inferred from satellite products. And well, there's a lot of similarities. You know, Amazon is more productive than other regions and the like. But there are also discrepancies. And what hasn't happened here yet is to learn from the observational data directly. That's ongoing work. So the hope is that having a good mechanistic model that out of the box gives us a reasonable simulation of climate, that now we can use the remaining mismatches to reduce this further to achieve hopefully a very good simulation of, in this case, the land biosphere. Maybe we'll leave the part of how do you actually reach people with this in the end to the discussion. I think there is a large space for machine learning tools of quite a different flavor. That'd be fun to talk about. I'll leave that here. I leave my conclusions up and we can talk about the rest. Let me just, before I go back to the conclusions, simply say a word about who funds us. Eric and Wendy Schmidt are our main funders through Schmidt Futures. There are various other grants from the Heising-Simons Foundation, National Science Foundation, Department of Defense in the United States, Defense Advanced Research Project Agency funds part of this work. And there have been various other private funders, especially Charlie Trimble has been a strong supporter from the outset. So I leave the conclusions up here and I hope we can simply have more discussion. So thank you.
Thank you. So thank you, Professor Schneider, for this informative and very engaging talk. We have a perspective on, I guess, the computational issues with the current Earth system models and perhaps some exciting ways forward. I'll ask people in the audience first if there are questions here. Rama, go ahead.
Hi. So my question was about your large eddy simulations. How do you account for droplet growth? And in particular, how do you distinguish between suspended droplets and rain?
Yeah, so all microphysics remains parameterized, right? And maybe the first thing to say is that whatever you do for these processes, what you should do is use the same parameterization in the single color model that you train and the LES, so that while we surely get this wrong in some fashion, hopefully we get it wrong in the same way and can still learn about the dynamics. We have various microphysics schemes we have been using. The simulations I showed, there was actually a combination of them. There was Seifert Beamhang 2-moment microphysics and simpler 1-moment microphysics for the simulation of the ice phase. It's 1-moment microphysics that it's strongly physically motivated, somewhat inspired by Kessler and Grabowski. And we are working on more complex microphysics. I should say similar approaches you can use for microphysics. So what we're doing on the microphysics side, well, we try to develop approaches that are more generally scalable, that where you can adapt the complexity to the data you have. So higher moment approaches, one student is working on collocation methods for that. And the way to get at the ground truth, we don't have a real ground truth, but the closest approximation of a ground truth we perhaps have, or that we have used, are these Lagrangian particle simulations, super droplet simulations. Those we have used pretty extensively for calibrating microphysics schemes and trying to learn how to represent microphysics. But as you know, the hard part of microphysics is the real ground truths you don't really have. I mean, it's not as accurate as what we can do for the fluids problems.
Hi, can you hear me?
Yeah.
Okay, yeah, thanks a lot, first of all, Professor Schneider, for a very, very engaging and informative talk. I'm way out of the field, and so let me just ask you 2 questions. One is just about references. For someone who knows next to nothing about your approach, So there was the Great Physics Today article you mentioned, but next up from there, is there one reference you would say one could read to get a basic introduction to your approach?
Yeah, there was a paper that kind of kicked this whole thing off. It was called Earth System Modeling 2.0. I think it was 2017 NGRL. I think that's a bit more technical and outlines the approach on how we view the learning from data should work. And that was really the beginning of this work. I mean, that was before we had figured out how to make the learning efficient and the like, but I think the general approach that we're pursuing is outlined there.
Okay, thanks. And my second question was, you kind of skipped over that, I think, for lack of time, about how these learning approaches, etc., might also help vis-a-vis engaging with you know, the larger community or policymakers, etc. Could you walk us through that slide of yours, please?
I mean, this slide here was mostly a cartoon, but I can explain that and then we can talk about the approaches I would think we could use here. So, okay, sorry, my screen real estate. No, I can't see my own slides here, the way this is set up. Hang on, maybe you can see this well enough if I just, let's do it this way. So the way I view how this translation to what people need should work is that you have a back-end climate model, and ideally that in the end provides an API that people can hook into to get to the back-end climate information that you need to drive, for example, say a flood forecasting model. And the Google Flood Forecasting Initiative has been modeling flooding in India. Nowcast has been trying to nowcast floods in India. They've built, I think, a really good model that takes weather data as input, river gauge data as input, and translate this into extremely granular flood nowcasts, flooding in a few hours ahead. And so those types of, and it's likewise a hybrid model that uses machine learning approaches together with physical models. So if you have those types of front ends, you can just take now a good climate model with quantified uncertainties as back end and use that simply to replace where current weather data are entering with simulated weather data of a different climate to assess flood risks rather than flood forecasts. Wildfire, you could imagine similar approaches. So my vision here would be that we have an interface that allows you to query a climate model at granular detail, and that gives you our standard backend climate information that then is converted into what you actually need if you plan development, if you try to simulate building energy demand in a warmer world and the like, which is pretty specific information. Say for building energy demand, you would want to get good statistics on extreme heat waves, say two-week heat waves. What does it look like 30 years from now? Buildings we are building now will most likely last 30 years. You like to plan for it. And for different sectors, you need different information, and I would envision different front ends that are specific to the sectors that are built on a climate modeling backend. And you need machine learning tools for that in many places, actually. You need to, we're spitting out these large eddy simulations where we want them and when we need them. We have developed algorithms for finding optimal places where they're most informative. But so in principle, you get very high resolution simulations wherever you are, but of course that's really expensive. So what I think you would want to do is emulate this process. You do it a number of times, but you want to build emulators that make this cheap. And so you need machine learning emulators for downscaling effectively trained on, say, large eddy simulations. You need machine learning tools, I think, for quantifying extreme events. It was a bit after Balaji's talk, the questions that came there. You know, Balaji mentioned precipitation is harder than other statistics. Yeah, sort of. I mean, it is, but it is non-Gaussian, but you can transform it to being closer to Gaussian. Start with taking a logarithm, it gets closer to Gaussian. And so A, transform to spaces where learning about these statistics gets easier, and then B, you want to learn about extreme events. And this is actually something we're currently working on how to do this. So just emulating the mean isn't all that interesting. You want to emulate the tails of the distribution. And there are ways, for example, to combine ideas from large deviation theory with machine learning approaches to get at the tail. So there's a lot of space for ML on that front end applied side as well. And that has mostly to do with downscaling from coarse to high resolutions. How do you get the relevant statistics for each sector? And especially because most losses are in the tails, how do you get the tails of the distributions right?
Okay, any other questions in the audience here? Go ahead.
Hi, it was a very nice talk. So I have a one naive question. So are uncertainties involved in the prediction get reduced when you use the artificial intelligence? And if it is reduced, I mean, what is the order of reduction in the uncertainties?
Yeah, good question. So, well, yes, I hope these approaches we use will lead to reductions in uncertainties. I mean, saying in equilibrium climate sensitivity, we have almost factor 3 span from lowest to highest sensitivity models. Now, how far can you reduce it? I'd say, I mean, the goals we've set for ourselves is reduce errors in, say, precipitation statistics, biases in precipitation by a factor 2. That I think is definitely achievable. Factor 2 uncertainty reduction. How much more is achievable? I hope more is achievable, but maybe ask me again a year from now when we have a better sense. I don't know how much more you can reduce it.
Yeah, Sarvanan.
I had a follow-up question about, you said you could estimate UQ for structural uncertainty. I'm just curious how you do it for like let's say climate in the year 2100. How do you estimate the effect of structural uncertainty on something like tail risk? Can you actually do that?
I mean, there are the famous unknown unknowns that you probably can't do anything about, right? But before hitting the wall with those, I mean, what you can do is, I mean, the structural model error you just estimate with existing data, right? So whatever you can learn from the existing data is ultimately the limit. How we actually do it, we have tried various approaches towards that. There's and various approaches can be successful. We have used dictionary learning approaches, like Balaji was talking about before, discovering differential equation terms. We have used Gaussian processes for that purpose. We have used deep learning methods, random features, neural networks for that purpose. There's a few general things we have learned that are important, and maybe more than anything, what is important for doing this well is that you need to basically use L1 regularization. The reason is that, excuse me, if you don't force the structural model errors to be zero, where data do not force them to be non-zero, what will happen is you just learn non-zero errors simply because you can that project onto the null space of the data. And that can be terrible in leading to misrepresentation of uncertainties. That's maybe the core lesson that we have learned there, is that you really need to force the errors to be zero unless the data dictate it to be otherwise. Will you in the end have complete uncertainty quantification? Say I would hope on timescales of a few decades. I hope yes. On longer timescales where really surprising things can happen, ice sheet instabilities and the like, that perhaps you cannot learn from a present data, that will probably remain somewhat unquantifiable.
Okay, quick follow-up. Even for next few decades, I mean, basically, at some point you have formulas. You're talking about sparse parameterization. So are you assuming implicitly that there is the set of formulas you're looking at spans the space of possible formulas? Or do you have to make that assumption?
Yeah. I mean, there's a universality assumption.
Okay, thank you.
But again, I mean, the results I showed you were for scalar parameters and sort of hand-guessed formulas. Those I wouldn't necessarily trust. But if you put more expressive functions there, I think I mean, this is the approach that has worked in fluid dynamics for 120 years or so, and I believe it will work here as well. Can I prove it? No.
There's a question in the chat. So Mercy, do you want to just unmute yourself and ask?
Hello, am I audible?
Yes, you are.
Yeah, I was wondering, like, is there a way to represent aerosols into climate models through AI? Because finally, we always say that there is aerosol influence the radiations and the clouds, and that is how the climate has been influenced. So, like, we find it difficult to represent aerosols in the normal models because it is very heterogeneous, both spatially and temporally.
I mean, a challenge with using machine learning tools for aerosols is, again, the lack of data. That we don't have a computational ground truth. We don't have observational ground truth that's easy to parse, or the observations we have are, they're a convolution of many factors. Aerosol optical depth we have some idea about, but say details of the hygroscopicity distribution of aerosols globally, we do not have. I think, so the aerosol models we're currently working with are fairly standard. What we have discussed doing is parameterize aerosols in different ways from how it's usually done. Say, not necessarily parameterize them in terms of chemical species, sulfate and the like, but what really matters for nucleation in the end is the hygroscopicity, for example. So can we simply represent aerosols through hygroscopicity classes and provide sources for hygroscopicity classes and reactions and the like? And there's probably, so what I could imagine one could do is take a highly resolved chemistry model that models many reactions important for aerosols, and then emulate that with AI tools and say map it to some latent space where something like hygroscopicity might be the relevant variable. We haven't done that. Danielle Jacob at Harvard, who's been working on GeoChem a lot, has thought about such approaches. And they probably have done some. Actually, I'm not quite sure what they have done, but I suspect they have done things in that direction. We haven't.
Okay, thank you. So basically, what I understood is that we need more observations of aerosols to actually make them into some form in which we can enter them. You mean to say that also?
Definitely. The hard part is that these observations are really hard to get, and maybe the ones we most need are impossible to get. I mean, getting details of aerosols inside clouds, it's just beyond what we can observe right now.
Okay, thank you.
One final question, Professor Schneider. So you're expecting your model to be running in next year, I guess. What kind of speed are you looking at, to simulate, say, 100 years? Can you give us an idea? Computational time?
So we want an atmosphere, so an AMIT type configuration to be running this year. And well, we'll have to see. I mean, right now our model is pretty slow. It's pretty slow for various reasons. I mean, one simply is that the parameterizations we use are parametrically sparse and simple in that regard. Computationally, they are a good bit more expensive than what people usually do because of these prognostic terms. we also have a lot of software engineering to do on the Dicor that before that's really as fast as we want it to be. Yeah, difficult to say, but I think I mean, in some ways, the answer to your question is turning the question around. You just, because you have this Cortex scaling of flops with resolution, you simply pick the resolution that allows you to do 100 years in a few days, right? And then the question is, what resolution will that be? I don't quite know yet. I would hope it's probably around 100 kilometers or so in the atmosphere and horizontal. But the vertical resolution, I should say, is pretty fine that we use because we found that to be definitely near the surface. We found that to be important for good parameterizations of clouds.
Okay, thank you again. There's, I guess, lots for us to learn and think about from your talk. So again, join me in thanking Professor Schneider.
Yeah, my pleasure. Thank you.